Yes, good morning, students. So today we are going to discuss the topic D block and F block elements. Right. So are you able to see the screen? Okay, so we'll start with the topic D block and F block elements. Okay. So first we'll see the electronic configuration of D and F block elements. So D block. So what are D block elements? So these are those which have partially filled penultimate d orbitals. What do you mean by penultimate d orbitals? It is the second last orbitals. Okay, so D block elements are those which are partially filled penultimate d orbitals in either their ground state or in their common oxidation state. So what do you mean by penultimate? Is nothing but your second last orbitals. Okay, so these are partially filled in your second last d orbitals. Okay, so these are d block elements. So what is the general electronic configuration of these transition elements? So d block elements are also called as transition elements. So what is the general electronic configuration? It is n minus 1. So n minus 1, it represents your penultimate, okay, penultimate orbitals, that is your second last orbitals. So that is n minus 1, d 1 to 10, ns 1 to 2. So this is the general electronic configuration of d block elements or your transition elements, where n is your outermost shell. Okay. So these are also called as what? As I discussed, it is called as transition elements, as their properties are in between that of S block elements and P block elements. So they represent the transition. So as their properties are in between, so where they are placed, so S block is to your left side of the periodic table, P block are to your right side of the periodic table. So in between S and P block, D block elements are residing. So these are called as transition elements. So their properties are in between that of S block and P block. So they are called as transition elements. So some of the elements like zinc, cadmium, and mercury, they do not show properties of transition elements to any appreciable extent except forming complexes. So these are some of the elements where do not show the properties as that of transition elements, but they form some good complexes. Okay. So in this transition elements or D block elements, it consists of 3D, 4D, 5D, and 6D orbitals. Okay. So these are eventually filled. So the transition element, they consist of 4 series. So 3D, 4D, 5D, and 6D orbitals. Now, what about the atomic radius in, okay, so atomic radius of transition elements is smaller than that of S block elements and larger than that of P block elements. So as you go across the period, okay, as you go across the period, what happens to atomic radii? It goes on decreases, right? So as compared to S block elements, your transition elements, they have smaller atomic radii, and they have larger atomic radii as compared to P block. Right. So you know how atomic radii varies across the period. So the irregularities in the electronic configuration. So there are some irregularities shown by some of the elements like chromium, copper, okay, then molybdenum, then palladium, then silver and gold. Okay, so these are so this irregularities of the electronic configuration of some of these elements can be explained based on the extra stability of half filled and completely filled orbitals, then the other d orbital configuration. So you know, for example, chromium. Okay, chromium, the electronic configuration is 24. Okay, and copper, it is 29. But it so it has a, so what it does for it occupies a stable it occupies extra stability by filling the orbital. So instead of 4 electrons, okay, so they will be singly, okay, in the d orbitals. Okay, I'll just show you. So what happens? The copper, So copper instead, chromium instead of, okay, chromium. So chromium, okay, when you are filling the electrons, so they will be, so it will occupy in such a way that it will be extra. So this will have extra stability. So it will be half filled chromium, because as it is having 24, but so what it will, the electrons will be arranged in such a way that it will have extra stability. So because of the extra stability, some of the elements, they show irregularities. Okay, so these are certain elements. So based on this, we'll solve some questions. Transition elements are. So what are transition elements? What are transition elements? Yes. What they are transition elements? S block, P block, D block. Yes, please answer. What are it is D block. Yes. So it is D block, right? Transition elements are also called as D block elements. Okay, right? So we'll go for the next one. An atom with atomic number 21. Okay, it belongs to the category of which it belongs to which category? Atomic number 21. So according to Aufbau principle, you have to fill the electrons. Okay, you have to fill the electrons. Yes. Yes. So 21. So 21, it is the atomic number of scandium, right? Scandium. So the argon is 18. Okay, argon is 18 electrons. Argon is 18 electrons. Then further 3d1, 4s2. So the electrons are filled in d orbitals. So it is C. Okay, the answer is C. D block elements. It falls into D block elements. Scandium. Your D block element starts from 21. Scandium. Okay. So 18, 19, 20, 21. Okay, argon is 18, 3d1. So the electrons are filled in d orbitals, right? So it is the element, okay, so it falls into D block. So next, we'll go for the next one. The first transition element is, yes, we discussed just now. So which is the first transition element in 3D series? It is, yes, it is scandium, right? It is scandium. Yes, correct. Okay, it is scandium. So which of the following is a non-transition element? Non-transition element meaning it is not a D block element. It is not a transition element. It is other than D block. It is either S block or P block element. So which is a non-transition element? Which is a non-transition element? Yes, lead, right? Lead is a non-transition element. So it comes into P block. So lead is a non-transition element. Okay. So others, cobalt, cerium, okay, Ag, these are okay, these are D and F block elements. Okay, so these are the cobalt and Ag is D block element. Cerium is a F block element. Okay, cerium. So we'll go for the next one. So we'll see the electronic configuration and oxidation state. So as we discussed, so there are 4 transition series elements in 3D, 4D, 5D, and 6D orbitals. Okay, so eventually they are filled. So, so as we discussed, so atomic radius of transition element is smaller than S block elements and it is larger than P block elements. So as you go across the, okay. So how is the atomic radius? How is the atomic radius? So atomic radius in a series, okay, first it decreases with the increase in atomic number up to middle of the series, and then it becomes constant, and at the end the series shows a slight increase. Okay, so this is the variation of atomic radii across your D block elements. So atomic radius down the group. Okay, you know, as you go down the group, what happens to atomic radii? It increases, right? So from first transition to the second transition series, but there is some irregularities. That is after second second transition series, there is almost same. Okay, so after the atomic radius, after second transition series, it is almost same. It is due to lanthanide contraction. So what do you mean by lanthanide contraction? We'll see in further slides. Okay, so remember, so atomic radii, as you go down the group from first transition series to second transition series, so it goes on increases. After second transition series, what happens? The atomic radii is almost same. What is the reason? It is due to lanthanide contraction. So all the transition elements, they are metals, right? All the transition elements are metals. They have HCP, CCP or BCC lattices. Means what? They have hexagonal close packing, then cubic close packing and body centered cubic packing. Okay, so they have such close packing structures. So atoms of transition elements are smaller than those of S block elements. So what is the reason why the atoms of transition elements are smaller than that of S block elements? Yes. The reason is C. Yes. Kumar has answered it as C. So it is, yes, Chandana. So usual contraction is size across a horizontal period. Okay, so you know, as you go across a period, so there will be decrease in the atomic radius, right? So S block comes first. So after that, D block comes. So because of that, that is one reason. Second is what? Orbital electrons are added to the penultimate D shell rather than to the outermost shell. Penultimate means second last shell. Okay. So both A and B are the reasons why transition elements are smaller than that of S block elements. Okay. So next is electronic configuration and oxidation state. So so if the number of unpaired electrons are more, if the number of unpaired electrons are more, then stronger will be the metallic bonding. Okay, and metals, as if this metallic bonding is stronger, then metals will be harder. Okay, for example, chromium, molybdenum and vanadium. Okay, so these are certain elements. So what happens if number of unpaired electrons are more? Okay, if the number of unpaired electrons, d electrons are more, so stronger will be the metallic bonding and metals will be harder. So these are some of the examples. So because of large number of valence electron, okay, if the number of valence electrons are more, valence electrons means outermost electrons, that is involving the ns and n-1 d orbitals in transition metals, then they have strong metallic bonding due to which metal possesses high density. Okay, so if the number of valence electrons are more in the outermost electrons, okay, outermost outer electronic shells, then they have strong metallic bonding. Okay, because of that, they have high density also. So in particular series, now if you go across a period, so what happens? The metallic bond strength increases up to the middle. Okay, it increases up to certain extent and then increases with the number of unpaired electrons. So if the number of unpaired electrons are more, then the metallic bond strength also increases. So tungsten, okay, tungsten, it has the highest melting point among the D block elements. So the melting point shown by tungsten is 3683 Kelvin. Okay, so this is the highest melting point shown by tungsten. So iridium, is another element, so which has highest density. Density is nothing but your mass per volume. So it has highest density, whereas scandium has the lowest, and it is called as the lightest transition element. Okay, remember this. So thermodynamic stability, if you see the thermodynamic stability, means if you compare the stability of this compounds, so it depends on what? It depends upon the ionization enthalpies. Ionization enthalpy is what? It is the amount of energy which is required to remove the this electron from the isolated gaseous atom. So if small amount, if the ionization enthalpy is small, of any particular metal, then stable will be the compound. So as So thermodynamic stability of any compounds, it depends upon the ionization enthalpy. If smaller is the ionization enthalpy of any metal, then stabler will be the compound. Okay. Then highest oxidation state of transition metals are found in fluorides and oxides, since fluorine and oxygen are electronegative elements. The highest oxidation state shown by any transition element is +8. So remember this, the highest oxidation state shown by transition element is +8. That is both osmium and rutherfordium shows +8 oxidation state. Okay. So most stable oxidation state is shown by osmium in OSO4. So this is a compound where osmium is showing the most stable oxidation state. So which is the highest oxidation state shown by transition element is +8. So which are the elements? It is OS, osmium and rutherfordium. Okay, Ru. So this is the highest oxidation state. So first members of each transition series, that is scandium, Y, lanthanum and actinium, do not show variable valency. Okay, they show only +3 oxidation state. So first member of each transition series, okay, they show only +1, +3 oxidation state. They do not show variable valency, or they do not show variable oxidation state. So the transition, so we'll see some questions. A transition metal ion exists in its highest oxidation state. So if a transition metal, it is exhibiting a highest oxidation state, then what type of behavior we must expect from that metal? Either it is acting as a chelating agent, a central metal in a coordinate compound, oxidizing agent, and a reducing agent. So what type of behavior is shown by a transition metal when it is having its higher oxidation state? Reducing agent means what? It reduces others and itself undergoes oxidation, right? Oxidizing agent means there will be, yes, it is acting as a oxidizing agent. Okay, it is acting as a oxidizing agent. Why? Because oxidizing agent was first only the metal will be in its highest oxidation state. Okay, so thus it does not lose any more electrons. So further it cannot lose any more electrons. So thus here any transition element, if it has higher oxidation state, okay, then it is acting as a oxidizing agent. So the answer is oxidizing agent. Okay, understood? So next, the electronic configuration of element which is just above the element with atomic number 43 in the same periodic group is. So you can see here I have attached a tabular. So if the electronic configuration of element is 43, just above the element, this is your Mn. Okay, Mn is placed with 25 is its atomic number. So what will be the electronic configuration? How do you write the electronic configuration? So which is the correct option? Electronic configuration of manganese, Mn. Yes. According to above principle, how the electronic this will be filled? Yes, Rakshita. Yes, Nandish, it is A. Okay, it is A. 1s2, 2s2, 2p6, 3s2, 3p6. First, you have 3d. Okay, 3d electrons will be filled, and then your S. Okay. First, your 4s electrons will be filled, then you will fill your d orbital. So, first, so it is 1s2. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d 5. Okay, so this is the electronic configuration. It is 1. Okay, it is A is the correct answer. Which of the following has electronic configuration? So which of the following? So these are certain elements, okay, with the higher oxidation state, Fe+3, Mn+3, Co+3, Ni+3. So which will have this configuration state after losing electrons? Yes. Yes, Lohit, Akash. Nuhu Sayed yet. It is C. Okay, it is cobalt. So you know Fe. Fe is what? Fe is 26. Okay. Fe is 26. If it is Fe plus 3 means what? Fe plus 3 means it will be 23 electrons. Okay, 23 electrons. Right. 3d6, 4s2. So it will be 3d4. Right. So it is 3d6. Then again what? Manganese. Manganese is 25. 25. Then if Mn plus 2 is there, Mn plus 3 is there, then it would have 22 electrons. Then it becomes 3d2. Right. Then if nickel is there, then it will be what? It will be 3d8, 4s2. Okay. Nickel is in plus 3 oxidation state. Then it becomes what? 3d7. Right, that is 25 electrons will be there. So if it is 28, it becomes 25. Then your cobalt is 27. Okay, 3d7, 4s2. Okay, then if it is cobalt plus 3, it becomes 3d6, right? 3 electrons are lost. So it is understood. I hope you are understanding the questions. Okay. So like this, you are going to find the electronic configuration. Okay, so this is the way you are going to solve this particular question. Of the following outer electronic configuration of the atoms, the highest oxidation state is achieved by which one of them? Means what? Highest oxidation state. How it will achieve highest oxidation state? If the number of electrons, okay, outermost electrons, if they have, you have to see the outermost, which is having the highest outermost electrons. Okay, if the number of electrons are more, so it can lose so many electrons and it can form the highest oxidation state. So see in each case, which is having the highest oxidation state. So this is number, it is 5. These are 7. Okay, these are 6. This is 4. So in which case it is B. So number of electrons, outermost electrons are 7. So maximum highest oxidation state shown will be plus 7, right? So it is N minus 1 D5 NS2. Okay, so answer is B. Yes, answer is B. So we'll go for the next one. Highest oxidation state of transition element is. So which is the highest oxidation state of transition element? We have discussed this. Yes. Nandish, Rakshita, Vidya, Abhishek, Chandana, Akash. Yes, it is plus 8. Okay. It is plus 8. It is shown by whom? It is shown by ruthenium and osmium. Okay. Ruthenium and osmium. It shows plus 3 oxidation, plus 8 oxidation state. Most common oxidation state shown by cerium are. So which is the oxidation state shown by cerium? So cerium is, okay, xenon 4F1, 3D1, 6S2. So either it loses 3 or 4. Okay, how many electrons are present? Either it can lose 3 or 4 of its outermost electron. So it can show plus 3 or plus 4. Okay, so cerium plus 3 is more stable. Cerium plus 3 is more stable than cerium plus 4. Remember this. So the answer is B. So it shows plus 3 and plus 4 because outermost electronic configuration is this. Okay, so it has 4 electrons. So either it loses 3 or 4. So the answer is B. Okay, answer is B. The oxidation state of chromium in the final product formed by reaction between Ki and acidified potassium dichromate solution is. Here, I'll write the reaction. Okay. Okay, understood. So what we are doing, we are acidifying. So chromium in the final product. So what is a chromium final product? What is the oxidation state here? So what is the done? Ki. Okay, Ki, potassium iodide is reacted with potassium dichromate in an acidified solution. So we have to tell, after writing the reaction, you have to see what oxidation state chromium has in its final product. It is C. Yes, it is C. Okay. So it is C. Which one of the following characteristics of transition metals is associated with their catalytic activity? Which one of the following? Okay, so elements which acts as catalyst should have the property to form what? It should have the property to form intermediate complex, okay, with the reactant. So if the reactants are there, so this catalyst should have that property to form the intermediate complex. Okay, so this happens when it happens if the element will be acting as a catalyst. So if the element is acting as a catalyst, so it should have what? Yes, the answer is D. It should have variable oxidation state. So any element, if for any element to if it is associated with the catalytic activity, okay. So the characteristic it should show is it should have a variable oxidation state. Means it should show variable oxidation states. So we'll see color of the compounds of transition elements. Okay. So most of the transition metal compounds are colored. Why they are colored? They are colored in both solid state as well as in aqueous state. What is the reason? The reason is due to the presence of incompletely filled d orbitals. Remember, so all the transition, most of the transition metal compounds, they are colored in aqueous as well as in solid state. What is the reason? It is due to the incompletely filled d orbitals. Okay. Transition metals are colored. So these transition metals, they are colored. Why? That there are two reasons. One is DD transition, another is charge transfer transition. So color due to DD transition is shown by which of the metals? So metals or the compounds containing D1, D2, D3, D4, D5, D6, D7, D8, D9 system. So from D1 to D9 system, okay, they show what? They show DD transitions. They show DD transition. The color is shown due to DD transition, and the compounds containing D0, D0 and D10 system. Okay, so whenever you have D0 system and D10, okay, the means what? D0 means what? There are no electrons. There are zero number of electrons in D orbitals. Okay, there are no or zero electrons. And D10 means what? They are completely filled. Okay, they are completely filled. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So whenever you have D0 and D10 configuration, then they are colored. Why? It is due to charge transfer transitions. Okay. So there in this system, that is D0 and D10, there is the color is due to charge transfer transition, and there is no possibility of DD transition. So remember this, transition metals are colored due to two reasons. One is the DD transition, another is charge transfer transition. So DD transition is shown, or the color of color due to DD transition is shown by which transition metals which have D1 to D9 systems, and the compounds containing D0 and D10 configurations are colored due to charge transfer transition. So in this system, there is no transfer or there is no DD transitions occurring. Understood? So this is the reasons why transition elements are colored. So one more, potassium dichromate. So potassium dichromate is acting. Okay, potassium dichromate is a strong oxidizing agent in an acidic medium. So you can see here your chromate ions, they take up the electrons and hence it acts as a good oxidizing agent, right? You can see here Cr, which is in +6 oxidation state. It is been converted into, in the product, it is +3. Okay, so it is acting as a good oxidizing agent. Okay, it is acting as a good oxidizing agent. So chromyl chloride test, important chromyl chloride test. Okay, so chromyl metal chloride on heating with solid potassium dichromate and concentrated H2SO4, it gives red vapors of chromyl chloride. Okay, so this is the reaction. So see the reaction, go through the reaction. Okay, chromyl chloride test. So when a metal chloride on heating with solid potassium dichromate, okay, and concentrated H2SO4, this chromyl chloride test you have done in your laboratory, okay, for detection of chlorine, right? For detection of chlorine, you do the chromyl chloride test, okay, in your qualitative analysis, right? So action of heat, when heated to white heat, it decomposes. So when you heat your potassium dichromate, okay, it decomposes into K2CrO4 plus Cr2O3 plus oxygen. Okay, so there is evolution. So after decomposes your potassium dichromate, it decomposes with the evolution of oxygen. Okay. So some of the questions: when MnO2 is fused with KOH, a colored compound is formed. So the product and its color is. So I'll write the reaction: MnO2 plus 4KOH plus O2. Okay, it is fused with KOH, giving you 2K2MnO4. That is potassium permanganate. So this is potassium permanganate. So when this MnO2 is nothing but your pyrolusite. Okay, it is pyrolusite. So it is pyrolusite. So when you fuse your pyrolusite with KOH, okay, then K2MnO4 is formed, which is purple green in color. So what is the color? It is purple green in color. Okay. So most of you have answered it. Yes, it is A. Okay, it is A. So it is A. K2MnO4. It is purple green in color. Okay, potassium permanganate. Among, okay, these are certain compounds, transition metal compounds. So among this, okay, it is TiF6 2 minus, okay, COF6 plus 3 minus, okay, then Cu2Cl2 and NiCl4 2, okay, minus. So among these, the colorless species are, you have to tell which are the colorless species. Yes, which are the colorless species? It is, yes, it is A. Yes, A is the answer. So, you know the oxidation state of Ti. Okay, in Ti, F6 is plus 4. Okay, so there are no unpaired d electrons are present. So when Ti plus 4, okay, Ti to Ti plus 4, there will be 0. So there are, it is undergoing a D0 system. It is undergoing a D0 system. And in case of cuprous chloride, okay, Cu2Cl2, okay, your Cu will be is in plus 1 state. So number of unpaired electrons again. So Cu will be plus 1 state. So when Cu it is plus 1, it will be 0 system, right? So the d electron present in Cu plus is 0. So those TiF6 2 minus and Cu2Cl2, they have 0 electrons in the d system, and those they are having what? They are colorless. So the colorless species, while rest of they are having unpaired electrons. Thus they are colored. Okay, they are colored. The colorless species is, so among these also, which is the colorless species? Which is the colorless species? So you have to see the oxidation state. Okay, so the colorless species is C, Na3VO4. Okay, it is a compound of vanadium. It is a compound of vanadium. So vanadium in this is plus 5 state. Okay, and plus 5 vanadium, it will have no unpaired electrons. Oh, okay. So there are no unpaired d electrons, hence it is colorless. So the answer is C. Okay, answer is C, vanadium. Okay, so it is, yes, the answer is C. In an acidic medium, CrO2 4 minus changes to CrO2 4 minus in an acidic medium. So chromate ions are changed to what? they are so in the presence of H plus, acidic medium means H plus. Okay, what it gives you? It will be, yes, Naveen, Lohit. Yes, it is A. Okay, it is A. See, chromate ions are changed to dichromate ions. Okay, they are changed to dichromate ion in the presence of acidic medium. So it becomes Cr2O7 minus plus 2H2O. Okay, plus H2O. So this is orange in color, dichromate solution, and this is your yellow solution. Okay, so in acidic medium, it changes to dichromate ions. Okay, these are dichromate ions. So the answer is A. So we'll see the magnetic behavior. So, so due to presence of unpaired electrons in n-1d orbitals, most of the transition metal ions and their compounds are paramagnetic. Paramagnetic behavior is shown by some compounds which are having unpaired electrons. Okay, and these electrons, unpaired electrons, they will be attracted by the magnetic field. Paramagnetic behavior is shown by such compounds in wherein your elements, your electrons of that compounds are unpaired. Okay, and these electrons are attracted by magnetic field. So paramagnetic behavior is shown by presence of unpaired electrons. So those transition elements which have paired elements, paired electrons. So whenever you have paired electrons, then they show diamagnetic behavior. So whenever you have diamagnetic behavior, these electrons are repelled by the magnetic field. Okay, so remember these conditions. A paramagnetic substance is characterized by its effective magnetic moment. Okay, that is a mu effective, which is given by the expression. So this is the expression where it is given magnetic moment is expressed, that is square root of n into n plus 2 Bm. This Bm, it represents your Bohr magnetum. It represents your Bohr magnetum, and n, this n represents your number of unpaired electrons. Okay. So this above reaction relation, it is called spin only formula. Okay, it is used to determine the effective magnetic moment. So it is used to characterize the paramagnetic substances. Okay, it is given as effective magnetic moment. So remember this expression, very important. So this is very important. Okay. So it is given by what? Bm. Bm is nothing but your Bohr magnetum. Okay. So which of the following is paramagnetic? Now these are certain compounds wherein you have to tell which of the following is a paramagnetic among this. Yes. The answer is D. Okay, D, because potassium can exhibit as +1. Right. Potassium can exhibit as +1. So here oxygen is what then? +1 means oxygen here is -half. So it is oxygen is -half. So this is what KO2 is nothing but it is a superoxide. It is called as superoxide. Okay, it is called as superoxide. Okay, superoxide. So here oxygen carries what charge? The oxygen, it carries -half charge. Okay. So here oxygen, they also behave as free radicals. So here oxygen, as they have -half charge, they carry, they act as a free radical, which is having unpaired electrons. Okay. So hence it becomes paramagnetic in behavior. So remember this KO2, superoxides of oxygen. So it is the answer. Urja. Okay, so the answer is D. The answer is D. So the complex which shows a spin-only magnetic moment of 2.82 pm is. So which is a complex which shows. So what you have to do, you have to calculate the electronic configuration first of all these. Okay, and then you have to, the formula n into n plus 2 root of, right? So you have to add and you have to see which of this complex will give you 2.80 as the 82 as the answer. Okay. Nickel is what? Nickel is 28. Okay, so it will be 3D8 4S2. So nickel will be in each case you have to find out the oxidation state of nickel, and then you have to calculate the. Okay. Yes, what is the answer? Yes, the answer is B. Yes, most of you have answered it right. It is B. Okay, B. So I'll just show you B. NiCl4 2 minus. Okay, mu. How do you calculate? N into N plus 2. Okay, so you know NiCl4 2 minus. So your N plus, okay, 4 into minus 1 equals to minus 2. So minus 4 equals to minus 2. So x is equals to minus 2 plus 4 equals to 2. Okay, so oxidations, this is 2. So 3D8. So there are, okay, so number of electrons, this will be 2, right? So you have to write, so it will be 2 into 2 plus 2. Okay, so this will come to 2.82. So the answer is 2. So like this, you have to solve it. Okay. So next we'll see lanthanide and actinides. So the elements with atomic number 58 to 71, that is cerium to lutetium. Okay, so these are called as lanthanides. So immediately after lanthanum, that is Z is equals to 57. So after lanthanum, the elements are said to be lanthanoids or lanthanides. Okay, or lanthanons or rare earths. So these elements involve the filling of 4f orbitals and also called as 4f block elements or first inner transition series. So what is the general electronic configuration? It is xenon 4f 1 to 14, 5d 0 to 1, 6s2. Okay, this is the general electronic configuration, okay, of lanthanoids. So promethium, okay, this is a atomic number 61. It is only synthetic or man-made radioactive lanthanoid. So remember this promethium, okay, with the atomic number 61. It is the only synthetic or man-made radioactive lanthanoid. So because this lanthanum is closely resembles the lanthanoids, okay, it is also included among the lanthanides. Okay, for the general symbol Ln. Ln is a general symbol which is used. Okay. So the elements with atomic number 90 to 103. So that is thorium to lawrencium, which comes immediately after actinium. Actinium with atomic number 89. These are called as actinoids or actinides or actinons. So these are the elements which involve the filling of 5f orbitals. So these are also called as 5f block elements or second inner transition series. So what is the general electronic configuration? It is radon. Okay, then 5f 1 to 14, 6d 0 to 1, 7s2. So this is the general electronic configuration of actinoids. So the most stable oxidation state shown by lanthanoids is +3. So we were discussing about lanthanide contraction. Okay, so there is after second series, you can see that the atomic radius remains the same. What is the reason? It is lanthanide contraction. So the regular decrease in the size of lanthanide atoms and ions from La to La+3 to lutetium is known as lanthanide contraction. So what is the reason for lanthanide contraction? It is due to greater effect of increased nuclear charge than that of screening effect, which is attributed to imperfect shielding of one electron by another in the same subshell. So this is the reason why it is showing lanthanide contraction. So there is due to the greater effect of increased nuclear charge. Okay, so as there is increased nuclear charge, then that of screening effects. Okay, so you know what is screening effects. Okay, nuclear charge, these all we have discussed. So this is the reason for the lanthanide contraction. So what is actinide contraction? If there is regular decrease in ionic radii with increase in atomic number, okay, then it is in actinoid series, then it is called as actinoid contraction. So they include 3 naturally occurring elements, that is thorium, protactinium, and uranium, and 11 transuranium elements or transuranics, which are produced artificially by nuclear reactors. The dominant oxidation state of actinoids is +3, which shows increasing stability of the heavier elements. So most of the trivalent lanthanoid ions are colored. Okay, they are colored in both a solid state, that is due to what? It is due to the FF transition. So most of the trivalent lanthanide ions, they are colored. Okay, so they are colored both in aqueous as well as solid state. It is due to FF transition. So which of the following pairs have the same size? Yes, which of the following pairs have the same size? Which of the following have the same size? Yes, Nuhu Sayyad, it is A. Okay, the answer is A. So this is having 4D series, this is 4D, and this is 5D. Hafnium. Okay, hafnium is zirconium and hafnium. Okay, hafnium. So it is what? Zirconium, it is in 4D series, hafnium is in 5D series. Okay. So because of this, what you can see here, almost they have small size, same, the both the sizes are same. What is the reason? Due to lanthanide contraction. Okay, due to lanthanide contraction. So the zirconium, it comes in 4D series, hafnium, it comes in 5D series. So the answer is A. Okay, answer is A. So elements after atomic number 92 are called as, so the elements which are placed after atomic number 92, they are called as what? Atomic number 92. 92 is atomic number of which element? Yes, yes, it is of uranium. So after the element uranium, what are they called as? It is called as transuranium. Remember this, it is transuranium. Okay, the element atomic number uranium is 92. So after the atomic number 92, the elements which come, they are called as transuranium elements. So these are the elements which are used in radioactivity. Mish metal. Okay, important. What is mish metal? What is mish metal? What is mish metal? Yes, fast. What is mish metal? Yes, mish metal. It is an alloy of lanthanide, iron, and carbon. Okay, the answer is C. Mish metal. It is an alloy of lanthanide, iron, and carbon. The lanthanide contraction is responsible for the fact that why is lanthanide and contraction responsible? What is the reason? Yes, it is C. Zirconium and hafnium have about the same radii. It tells you about the, yes. Okay. Reason for lanthanide contraction is, what is the reason for lanthanide contraction? Yes, it is negligible screening effect. So it is due to the negligible screening effect of f orbitals. Okay, good. So we'll solve some of the previous year's question papers. Okay, we'll solve some questions. Second. Yes, you can see the screen.
Yes, ma'am.
Yes, okay. So we'll go through the first question. Identify the set of paramagnetic ions among the following. So this is 2020 question. So you have to identify the sets of paramagnetic ions among the following. Yes. Yes, most of you have answered it right. It is C. Okay, the answer is C. Titanium. So ions which contains, so paramagnetic behavior is shown by which ions? Which contains unpaired electrons. Okay, so here, so you can see titanium plus 3. Okay, so titanium plus 3, they have unpaired electrons. It is 3. So they have unpaired electrons in titanium. Then your copper plus 2 and manganese plus 3. So if you write the electronic configuration, okay, then you can see that there is there are unpaired electrons are present. Okay, unpaired. So next question, how many moles of acidified potassium dichromate is required to liberate 6 moles of I2 from an aqueous ion of solution of I minus? Yes, I'll write it here. K2Cr2O7 plus 6 Ki plus 7 H2SO4, giving you 4 K2SO4 plus 3 I2 plus Cr2SO4 thrice plus 7 H2O. Okay, so how much moles of acidified solution is required? Okay, so here you can see 3 moles of iodine. Okay, 3 moles of iodine. Here, 3 moles of iodine. You can see. Just a second, I'll change the color. So 3 moles of iodine. Okay, it requires how many moles of potassium dichromate? 1 mole. Okay, then what they have asked? 6 moles. So if 6 moles of I2 requires how many mole? It requires 2 moles. So the answer is A. Okay, understood? I hope you are understanding it. Okay, so next, Cu2Cl2 and CuCl2 in aqueous medium. Okay, so what is the correct statement? Cu2Cl2. So the answer is A. Okay, the answer is A. So in Cu plus 2, so Cu plus 2 is more stable than Cl2. Okay, here it is plus 2. So it is more stable than Cu plus 1. Okay. So because smaller the size, you know, Cu plus 2 size is smaller. Okay, as compared to Cu plus 1. Cu plus 2 means what? 2 electrons are lost. So the size in Cu plus 2 is smaller as compared to that of Cu plus 1. So because of this, in aqueous medium, hydration enthalpy, you know, hydration enthalpy. So hydration enthalpy depends on what? It depends upon the small size. Okay, it depends upon the size of the cation. So smaller the size of the cation, greater will be its stability. So Cl2 is more stable than Cu2 Cl2. Okay, so the answer is A. Answer is A. So the hydration enthalpy depends upon the stability. Okay, it depends upon the size of the cation. So smaller the size of the cation, more will be the hydration enthalpy and more will be the stability. Okay. So next, the elements in which electrons are progressively filled in 4f orbitals are called. Yes. Yes. Yes, they are called as lanthanoids. Okay. So the electrons, when they are filled in 4f orbitals, okay, they are called as lanthanoids. So halogens, you know, they are filled in what? They are filled in p block elements. Then transition elements, they are filled in d block elements, right? Actinoids, it is 5f. So it is lanthanoids. So they are filled in 4f orbitals, right? Correct. So next, incorrect statement with reference to cerium, that is atomic number 58 is. So incorrect statement with reference to cerium is. So it is A. Okay, cerium plus 4 is a reducing agent. So cerium. So incorrect statement is A. Okay, cerium plus 4 is a reducing agent. Cerium plus 4 is a oxidizing agent. It is a oxidizing agent. So this statement is wrong. Since it cannot attain oxidation state higher than that. So you know cerium, it can attain maximum oxidation state is plus 4. Okay, so it cannot attain more oxidation state or highest oxidation state than this. Okay, due to this, there will be decrease in stability. So Ce plus 4 is a reducing agent is a wrong statement. Okay, so it is a wrong statement. So the answer is A. Answer is A. Next, a mixture of NaCl and potassium dichromate is heated with concentrated H2SO4. Deep red vapors are formed. So which of the following statement is false? So which of the following is a false statement? Yes. Sixth, the answer is C. Okay, the answer is C. That is vapor contains Cr2, CrO2, Cl2 and Cl2 only. Okay. So the reaction, so what happens here? So it forms a deep red vapors. Okay, it forms a deep red vapors of Cl2, CrCl2 only. Okay. So the false statement is this. So it and Cl2. So it is not together. So when it is passed into sodium hydroxide solution, okay, yellow solution of sodium chromate is formed. Then further it is treated with what? It is treated with lead acetate. So when it is treated with lead acetate, it gives you a yellow precipitate. So this is correct. So it gives you yellow solution is correct. So the vapors contain CrO2, Cl2 and Cl2. It is wrong. So the statement is C. Okay, the false statement is C. So last one more question will solve. Which of the following statements is wrong? In highest oxidation state, the transition metal shows acidic character. Mn plus 3 and CO plus 3 are oxidizing agent in aqueous solution. Metals in highest oxidation states are more stable, and oxides in fluorides are fluorides. All elements of 3D series exhibit variable oxidation state. So which is the correct answer? So which of the following statement is wrong? So the answer here is D. Okay. The answer is D. That is all the elements of 3D series exhibit variable oxidation state. So this is a wrong statement. Okay. This is a wrong statement. So, so here what happens? Zinc. Okay. So you know zinc. So zinc contains what? Zinc contains completely filled d orbitals, right? So it exhibits a stable electronic configuration. Therefore, it does not easily lose electrons. So when you're talking about D with respect to this elements, D block elements. So you know zinc is 30, right? Zinc 30. So it configuration is completely filled, and therefore it does not lose its stability. Okay, it does not, it is already stable, so it does not lose its stability by losing the electrons, hence it does not exhibit variable valency. Okay, so the answer is the false statement is all the elements of 3D series exhibit variable oxidation state. So this is the false statement. So by this we have completed the chapter D and F block elements. So I hope you have understood today's session. So we'll stop it for today. So we'll meet in the next class. On Monday, we'll meet. Thank you. Have a nice day.
Thank you, ma'am.